Wastewater and the byproducts from food production and consumption are rich in biodegradable organic contaminants, and for this reason, they are also rich in chemical energy. There are biological, fermentative, and bioelectrochemical processes that make it possible to transfer this chemical energy to a conventional renewable energy carrier. In this lesson, we will look at the methods for recovering biochemical energy from wastewater. The chemical energy of organic matter is quantified in terms of COD or chemical oxygen demand, an aggregate measure that assesses the amount of oxygen needed to oxidize organic molecules. COD is therefore a measure of the electrons that these molecules can donate to a final acceptor, generating useful work. However, for this energy to be usable by humans, it must be converted into a conventional energy carrier. In this lesson, we will focus specifically on the biological processes capable of carrying out this conversion. These processes have a long history that dates back to the last century. The most well-known and widely used bioprocess is anaerobic digestion, which produces biogas, a mixture of carbon dioxide and methane, and does so through a complex degradative chain. Biogas is an excellent biofuel that can be used directly in boilers or in combined heat and power systems, or it can be converted into biomethane using well-established technologies capable of separating it from the biogas, known as upgrading technologies. Among these is the possibility of converting the CO2 present in biogas into methane by reacting it with green hydrogen. This is a bioprocess carried out by hydrogenotrophic anaerobic microorganisms that achieves three goals. It allows for the upgrading of biogas, it increases the amount of biomethane produced, and it makes it possible to absorb peaks in non-programmable renewable energy production in a distributed manner across the territory. Anaerobic digestion is a process widely used in Italy and throughout Europe. According to the GSE, in 2023 there were more than 2,300 biogas plants operating in Italy, capable of generating about 1,400 megawatts. Meanwhile, according to the European Biogas Association, the production of biogas and biomethane covers about 7% of Europe's natural gas demand. In addition to anaerobic digestion, there are other fermentation processes that use microorganisms with specialized metabolisms, allowing certain organic substances to be converted into liquid biofuels, bioalcohols. For example, bioethanol can be produced with good yield by fermenting simple sugars extracted from corn or sugarcane. Overall, the process consists of a phase where sugars are extracted from the biomass through chemical, physical, and enzymatic methods. Then comes the fermentation phase, which uses yeasts such as Saccharomyces cerevisiae, followed by the distillation and purification of the fermented product. The production of bioethanol is widely used, with nearly 1,000 plants worldwide and an annual European output of 5 million cubic meters. A fermentation process carried out by bacteria of the Clostridium genus is also capable of fermenting sugars and other organic acids to produce biobutanol through the acetone-butanol-ethanol fermentation process. Despite the construction of several commercial plants during the last century, the process has gradually been abandoned, since producing butanol from fossil sources has proven to be more economically competitive. Biomethanol and biopropanol can also be produced through specific fermentation pathways, which still do not have significant commercial applications. It is also possible to promote the formation of biohydrogen by stopping the anaerobic digestion process at the stage of volatile acid production, known as dark fermentation, which is accompanied by the release of hydrogen. Although the process is well understood, the conversion yields are low and the stability of the process is still limited, so it cannot yet be considered ready for scale-up. All these biofuel production processes are particularly efficient when they use biomass rich in chemical energy, such as corn or agro-industrial byproducts like molasses or whey. The biofuels produced in this way are called first-generation biofuels, and their production competes with the use of the same biomass for human or animal consumption, thus creating an interconnection between the food market and the energy market, the so-called food or fuel dilemma. Alternatively, fermentable organic substances can be extracted from organic waste, crop residues, or plants grown on marginal lands not used by the food industry, thus producing the so-called second-generation biofuels. Second-generation production is hindered by the greater complexity of the processes and the lower yield, which make them less economically viable. However, they are in line with the objectives of the European strategy outlined by the Renewable Energy Directive. Finally, it is possible to convert the chemical energy of organic matter directly into electric current using bioelectrochemical cells. These are biological batteries made up of two compartments separated by a semi-permeable membrane. Inside the anode compartment, microorganisms develop that are able to oxidize the organic substances in the wastewater, transferring the electrons to the anode instead of to a final acceptor. To balance the charges, protons migrate through the membrane toward the cathode compartment. From the anode, the electrons then move toward the cathode, where they are transferred to a final acceptor, typically oxygen. This process is therefore able to transform chemical energy into electrical work. Although the process is still being optimized, there are currently some pioneering applications in small plants powered by agro-industrial wastewater. In summary, the mature biotechnologies for converting the chemical energy of organic residues and wastewater into renewable energy carriers are the production of first and second generation biogas and biomethane, and the production of first generation bioethanol. The other technologies are still either technologically immature or not economically viable, and their future development will depend both on political decisions, such as the adoption of subsidies, and on process improvements that increase their yields. In addition, multi-product biorefineries are being developed that aim to also utilize the non-fermentable fractions of biomass, thereby improving the economic and environmental sustainability of second-generation biofuels.